All right, so here is where we're going to learn how to do the rules on integrals here in 7.3. So we have two different integrals where we've seen a little bit of the notation before. So the first integral we're going to talk about is one where we have numbers on the endpoints. And we saw it in the definition for the fundamental theorem of calculus. Okay, so this reads the integral from a to b, f of t dt. And this is called a definite integral. So it has a beginning and an end. It's going to give us an actual answer. Okay, and then we also have one that doesn't have anything. This is the integral of f of x dx, and this is called an indefinite integral. Okay, so we're going to write down all the rules that you need to know for antiderivatives here on the first one. Okay, so the first one we're going to use is x to the n dx. And so when we did derivatives, we subtracted. So with antiderivatives, we're going to add. Okay, so we're going to add to the exponent, and instead of multiplying, we're going to divide. Okay, and then anybody who's taking calculus knows this, but anytime we have an integral that's indefinite, you're going to always have plus c. So plus this constant. So there are multiple integrals that you can get. So we could have this integral plus 2, minus 6, minus 25.36635, blah, blah, blah. So that always works. Okay, but there's this side note on this one. Assuming n is not equal to -1. So this is a big deal. Okay, and a lot of my students forget this. Okay, if you get n is equal to -1, which gives you 1 over x, you get a different rule. It's the natural log of the absolute value of x plus c. So I get students that will write parentheses, but it's actually these absolute value pieces, and that's very important. Okay, our friend e to the x, just like when we took the derivative, we get e to the x. We take the antiderivative, we get e to the x. All right, here's the one that everyone forgets. Just like when we did derivatives, we also forget it with antiderivatives. Normally, we multiply, we're going to divide. Again, always easy to forget. Okay, two other rules that we're going to add on. One is the sum difference rule. Just like you would think it would be, just like it was with derivatives, it is also with antiderivatives. So if we are asked to take the integral of multiple terms, you are welcome to take them apart and take the integral of each one. So you can separate them if you want to. Oops, I always kind of forget that they need dx's at the back. So they're supposed to have dx's there. It's easy to forget. The other one I've been kind of prepping you guys for all semester. It's called the constant multiple rule. And we kind of just did it in our head before when we were doing derivatives, but it's going to really come in hand when we do antiderivatives. So this one's saying if we have a constant out front, any number out front of our function, you are welcome to put it outside of your derivative, or your antiderivative, sorry, and then take the antiderivative of the function. You'll see where this comes in handy in a little bit. All right, so let's do some antiderivatives. All right, so we're going to take 3x to the 5th plus 4x squared plus 5 plus 7 over x dx. So you're going to see a lot, sometimes on web work, sometimes on my work, and sometimes on the tests. All depends. You're supposed to have a parentheses around the entire function and then have dx. You're going to see me drop it. You can drop it. I'll forget it a lot. Okay, but technically the whole function's supposed to be in parentheses, and then it says dx for you're going to take the antiderivative of this whole thing. Okay, so if we're going to take the rule, write the rule down here in the corner, n plus 1 over n plus 1, that's the first one we're going to use. Okay, and so we get that 3x to the 5 plus 1 over 5 plus 1. So I'm writing it with the rule right now. Plus 4x to the 2 plus 1 over 2 plus 1. Here's one of those shortcuts. Anytime you have just a number, you get to just attach x to it. Okay? Because you're getting that 0 plus 1 whole idea over 0 plus 1. Okay? So that's where that comes from, but it just becomes x, and it's a little easier if I just write x. Okay? And then this last one is that rule, the 1 over x rule. So 1 over x turns into natural log of x. So you see I'm writing all the rules on the bottom that we need. Plus 7 goes out front. Natural log, absolute value of x. Now I'm going to cram that plus c in the back. So now I just need to simplify. So I get 3x to the 6th over 6 plus 4x cubed over 3 plus 5x plus 7 natural log absolute value of x plus c. One other thing you can do, we can simplify this 3 and this 6. Okay, so we're going to get x to the 6th over 2, or 1/2 x to the 6th, whichever you prefer, plus 4x cubed over 3, or again, you can move that 4/3 out front, x cubed, however you like it, plus 5x plus 7 natural log of x plus c. Okay, so that's the answer for this one. Let me box that in as the final answer so you know. This is the final answer. Okay, on 7.3's web work, so I'm going to put this in blue. Note, 7.3 web work does not want plus c, but on test, Professor Shivers does. Okay, so only on 7.3. 7.4 will be a different story, but right now it does not want this plus c. Okay. All right, let's do another one. Example 2. Integral of the square root of 2x plus the cube root of 4x dx. Here's our friend square root and cube root. They haven't gone away. So the first thing I'm going to do is rewrite them. And by the way, if your integrals don't look great, don't worry about it. I've only taken years of math and done years of this particular calculus class. So my asses are pretty good at this point. So we're going to rewrite this first one as 2x quantity to the 1/2 plus 4x quantity to the 1/3. Okay. And here's where I'm going to be able to pull this 2 and this 4 out using that scalar rule. Okay, so I'm going to rewrite this as 2 to the 1/2 integral x to the 1/2 dx plus 4 to the 1/3 integral x to the 1/3 dx. So I'm using both those rules that I put at the end, the sum difference, and constant multiple. Okay, both of those came into play there. All right. The integral of 2 to the 1/2 is not something you want to attempt. Just leave it alone. Okay. X to the 1/2 is much easier. Okay. So again, I'm going to take it slow. I'm going to take x to the 1/2 plus 1 over 1/2 plus 1 plus that 4 to the 1/3 x to the 1/3 plus 1 over 1/3 plus 1 plus c. All right, so we're going to work this out a little bit. It's going to take a little bit. All right, so I'm going to switch this to the square root of 2. This becomes x to the 3 halves over 3 halves plus the cube root of 4 x to the 4/3 over 4/3 plus c. All right, so no fractional exponents still. And these guys down here are going to do some fun things for us. They're going to flip. So we're going to get 2 square root 2. This x to the 3 halves, well, let's put the 3 on the bottom first, actually. This x to the 3 halves, remember the 3 is going to stay. So this x to the 3rd stays intact. So I'm going to get the square root of x cubed. I'm going to fix that in a minute. Plus 3 cube root of 4. The 4 stays on the bottom. Again, that 3 and the 4 there flipped. And then again, the x to the 4th stays intact. So I get the cube root of x to the 4th. Okay, so I'm going to show you 2 different answers to this. One is that we get 2 square root of 2 x cubed over 3, oops, I forgot my plus c there, plus 3 cube root 4x to the 4th over 4 plus c. There is a way to make this simpler. So I'm going to circle it in a different color. So you could make this 2x square root 2x over 3 plus 3x cube root 4x over 4 plus c. That's if you simplify it. This is what you would get in an extra credit problem. So this extra credit answer. This would be total regular answer. So it's a little intense. All right, so let's get back to a little bit easier ones. All right, so we have the cube root of 2 times 3 to the x plus 4 times e to the x dx. Okay, so again, we're going to use those two rules again. We're going to put 2 cube root 3 to the x dx plus 4 integral e to the x dx. So we're putting those numbers on the outside. So we're going to get 2 times 3 to the x over the natural log of 3 plus 4 times e to the x plus c. So I probably could have written that a little nicer on that second piece. The first piece is totally fine. So let me erase. I'll write this one a little bit nicer here. So the second piece could have been just 4 e to the x. I kind of got a little crazy there. So that's the answer. So if you were to put it into one of the internet browsers that helps you solve one of these, you would maybe see 2 natural log of 3 because those are all actual numbers times 3 to the x plus 4 e to the x plus c. So either or is fine. Doesn't matter to me. All right. So we've done 3 definite or indefinite integrals where we needed those plus c's. So again, the plus c, important on the test. For 7.3 web work, not so important. All right, let's talk about some definite integrals. So we've seen definite integrals when we were doing our Riemann sums. Six x squared plus 2 dx. So we're going to start out really easy. Okay, so we're going to get 6x cubed over 3. So again, we're going to add 1. Whatever's on the top as the exponent is what goes underneath. That's the shortcut. Anytime you have just a number, put x with it. Okay, you could put a plus c here if you wanted. So I'm actually going to put it in the lightest color. I'm going to put it in yellow. You don't have to, because we're dealing with a definite integral. You're going to see in the book, they're going to put a line with 1 to 3. Okay, that's great when you're writing it in a book and it looks all neat and tidy. And mine actually kind of looks neat and tidy here. Okay, mine never looked neat and tidy when I was in college. My handwriting's so much better now. But I didn't like how it looked like an absolute value bar. So I changed it and I put little n's on mine. However you want to do it is fine with me. So you can put it where it looks like a bracket like mine. You can put it like an absolute value bar. However you like it is perfect with me. Okay, but the plus c doesn't have to be there because you're not going to input numbers for the c. Okay, so I'm going to make this 2x cubed plus 2x. Makes it so much easier from 1 to 3. So now we're going to use that fundamental theorem of calculus, which tells us we need to do f at 3 minus f at 1. Okay, well, this is technically f of x. We did that last section. Okay, so I'm going to put 2 times 3 cubed plus 2 times 3. That's my first one. And then I'm going to subtract 2 times 1 cubed plus 2 times 1. Okay, so when I do that, I get 60 out of the front parentheses. And I get 4 out of the back. And then I get 56. So I like to see you write out all the work where you put the 3's in, you put the 1's in, you give me the 2 numbers, and then I get the final answer. So I can backtrack if you make mistakes. All right, let's do example 5. We can still fit this on this whiteboard. We're going to go from 1 to 100, 1 over x dx. Okay, so the antiderivative of 1 over x is the natural log of the absolute value of x. Okay, again, if you are one to like to write plus c, write it. It's not going to hurt anyone. From 1 to 100. Okay, so if you want to, if this helps, write f at 100 minus f at 1. Especially in this section, it will help you, but you don't have to. So this one is going to take the natural log of 100 and subtract the natural log of 1. Because these are natural logs, again, you can round. We're going to round to 2 decimal places here. I get 4.61. The natural log of 1 is 0. So we get 4.61. All right, one more. Example 7. Okay, they give us a marginal cost of Q equals 5 minus 0.002 Q. And they give us a coordinate that it goes through. Goes through 1,000, 6,000. So there's my QP. All right, so they want us to find the cost. What's the cost equation? Okay, in order to find the cost equation, we're going to take the antiderivative of 5 minus 0.002Q. All right, so we only dealt with x's so far in our notes, but you're going to use whatever variable you have to make the d. So this one's got a q, so we're going to do dq. Okay, let's put in the parentheses here so you can clearly see, hey, there's my formula, there's my dq. I don't have numbers to put at the endpoints. We're not doing that yet. Okay, so I'm going to take the derivative. I get 5q minus you can't really see my point, sorry, 0.002 q squared over 2 plus c. Okay, so my cost equation is c of q equals 5q minus, now let's not leave that as a fraction with a decimal, 0.001 q squared plus c. Okay, now we need to worry about, we have this coordinate. Now that we've taken the antiderivative, we're going to take the coordinate and plug it into our function. So we get 6,000 equals 5 times 1,000 minus 0.001 times 1,000 squared plus c. So the whole right side simplifies to 4,000 plus c. Still have 6,000 on the left. Subtract, I get 2,000 equals c. And there is only one function that is the the cost function that goes through 1,000, 6,000. That is 5q minus 0.001 q squared plus, now we're going to plug in our 2,000 for c. So we're looking for a very specific function, which is this one right here. So we need to make an equation after we find that 2,000. So make sure that you really focus on the different problems here. If you have any questions, then make sure you ask them.